There we go. Alrighty, gang. Welcome back and congratulations on making it through the second test. You're about halfway through this course now. Today, we're going to enter into a kind of new unit where we're stepping away from like a detailed study of individual families of functions, right? So like test 2 is pretty much all specific families of functions. We learned about quadratic functions, polynomials, rational functions, radical functions. What we're going to do today is kind of stepping a little bit in spirit and feel back towards what we did at the very beginning of the course, where we're working with functions in general, rather than with a specific type of function. Namely, what we're going to talk about today are operations with functions. So here we go. Connect. All right. Let's go ahead and do the title card before I blather on anymore. So this is MAC1105, section 15, which is college algebra. And the date today is it the 3rd or 2nd? It's the 3rd, March 3rd. I was thinking it was the 2nd. But today, we're covering the section called operations with functions. So you may remember back when we introduced the polynomial section, I said that in a sense, polynomials are like the function version of whole numbers. What I meant by that is that polynomials form an algebraic structure called a ring, where if you multiply two things from that set, you get another thing from that set. Like polynomial times polynomial, always going to be another polynomial. If you add two objects from that set, you always get another object from that set. So such a structure is called a ring. What we're going to start doing today is exploring the algebra operations that people like to do to sets of functions. So just like you do algebra with numbers, right? You can add, subtract, multiply, and divide numbers. And when we talk about algebra, we let variables represent those numbers, and then we kind of study how those operations interact with the variables representing numbers. Today, as we talk about operations with functions, what we're going to start doing is trying to understand the algebra of functions. So instead of your variables representing numbers throughout here, we'll be using symbols like f and g to represent arbitrary functions. And most of the operations will be operations you're familiar with, like addition, subtraction, multiplication. But there will be one new special operation that to mathematicians is very, very beautiful, and that's the composition operator. So I'm going to try to give you some analogies. We'll work lots of examples. The only place to begin is just by saying what it is we're doing, right? So how do we define the operations of functions? What are the operations and how are they defined? So we're going to say is let f of x, g of x be two functions. I'm going to provide some rules that will allow us to form new functions out of f and g. In the same way you can mash together two variables to form a new number. You can form new functions by mashing together two functions. And the first kind of task we're going to have is to find the domain of those new functions. But let's go ahead. So one can form new functions according to the rules all right, and as you write this down, leave a little bit of space in the places I leave space. So what we're going to do is we're going to form a new function called f plus g. That's going to be the name of the new function, and it's going to be defined exactly how you think it is. We're going to define a new function called f minus g, a new function called f times g, a new function called f over g, and then the special one down here is the composite f of g. And some people read that as fog, and there's some silly jokes or mnemonics that will help you remember what each of these things do. So what's the rule? Well, if I want to form the new function that I choose to call f plus g, the only way it makes sense to do that is to say that f plus g of x. So this is the function notation that we're familiar with, right? Just like f of x here is the output associated with the function f when fed the input x. This notation with the parentheses is the same thing, not multiplication. This is not f plus g times x. This is the output that you get from the function f plus g when you feed it the input x. And the rule is, how do you find f plus g of x? Well, you take f of x and you add it to g of x. Shocking, I know. We're going to do the analogous thing for all of these. So the function f minus g is defined by the rule f minus g of x is f of x minus g of x. F times g of x. Here's where the notation might surprise you a little bit. Just remember what this function is. It's f times g. So what should f times g of x be? Well, it's the product of the functions f and g. So it should be f of x times g of x. F over g, this new function that we form as the ratio, is going to follow the rule f over g of x is f of x over g of x. And then the fun one down here at the bottom, the composite function, what we're doing here is we're saying I want to take f of g of x. So that's f of g of x. That's what you get when you plug the function g into the function f. So these are the rules. I said our first kind of task is going to be to understand what the domain of each of these new functions is in terms of the domains of f and g. So let me go ahead here and say this. If the domain of f is the set A and the domain of G is the set B, then these first three, there's a nice rule for the domain of each of these. The domain of each of these, actually, instead of me just telling you, let's see if we can think through it together. Imagine you have some number x and you want to plug it into this first function. What must be true about x regarding the domain of f and the domain of g? So if I want to plug some number in here, where must that number be coming from in terms of domains? Perhaps the question is too broad. Suppose you have some number like 2, and maybe 2 is in the domain of f, but it's not in the domain of g. Can I plug 2 into this function? Shut out or just type in chat. What do we think?
No.
No.
Very good. Yeah. So if 2 is in the domain of f, but not in the domain of g, then I cannot plug it in here, because to plug 2 in here would mean I'm going to plug 2 into f, I'm going to plug 2 into g, and I'm going to add them up. Well, if 2 isn't in the domain of g, then g of 2 doesn't exist. So let's return to the original question now. If I want to plug some number into this first function, what needs to be true of that number with respect to the domain of f and domain of g?
They're the same.
F to be equal to 0.
Let's see. I think I heard something in there that I think we're gonna, they're the same, almost. So we need that number to be in both domains, right? If the number is in one domain but not the other, then I cannot plug it in here. If it's not in either domain, then I definitely can't plug it in here. So what that means is that the domain of this new function, f plus g, has to be stuff that's in the domain of f and also in the domain of g. It has to come from the overlap of their domains. If you have something that's in one domain but not the other, you can't plug it in here. So that means that the domain of these is going to be A intersected with B. And remember what that intersection symbol means? It means we're taking the overlap. So if the domain of f is A, that's the domain of the first function. The domain of g is B, that's the domain of the second function. I want to figure out what the domain of f plus g is. Well, it's in order for a number to be in the domain of this function, it has to be in the domain of f, otherwise I couldn't plug it in here. And it also has to be in the domain of g, otherwise I couldn't plug it in here, which means it has to be in both domains, and that's the intersection. And just a quick reminder, the kind of visual representation of that intersection is this. And so if this is the set A and this is the set B, then the intersection of A and B is the overlap. It's the stuff that's in both. Let's think for a second about the domain of this guy. I didn't include him in that statement that the domain is going to be A intersect B for a reason. Suppose you have a number that is in both domains, it's in this intersection, but it is also a number such that when you plug it into G, you get 0. Is that number going to be in the domain of this expression?
No.
Good, why not?
0 can't be in the denominator.
Mm-hmm. Yeah, that's it exactly. So the domain here is going to be A intersected with B. Everything we said about these is still true here. You have to be in both domains in order to be plugged in, but then you have to get rid of the x values that make g of x equal to 0. So certainly in order to plug a number in here, I have to be able to plug it into both f and g. So it has to be an element of this intersection. But there's this additional restriction because g of x is downstairs. If a number makes g equal to 0 when you plug it in, then I cannot plug that number into this fraction because then we would be dividing by 0, like Lexi said. So that's the domain rule for this guy. Now the last guy, this is the fun operation, right? I said this is the one mathematicians really like. He's also the one that has sort of the most confusing domain rule. If I want to plug a number x in here, the first step, I know it seems backwards, but the first step is to plug that number into G. And then you're going to take whatever that spits out and plug that into F. That's how this works. If you plug an x in here, then first G is going to be done to that. Whatever G spits out, that's what we're plugging into F. So what I'll say here is, I'm not going to give you the full rule because it's a little bit complicated, but the domain here is the math word is subset, right? So subset meaning like a little part of the domain of the inside function G. So these are the different operations we like to apply to functions. The first 4 are kind of like toys. We're going to play with them. They're operations that we're familiar with because they're the same operations we do to numbers. There's nothing new or special there. It's just we're doing them to functions now. The last one, in addition to being relevant in this section, is going to be relevant in the next section when we talk about inverse functions. It turns out that this circle operator, the composition operator, it's called, is a nice way to define something like multiplication for functions. It's not multiplication, right? This is multiplication, but there's a sense in which this is a nicer kind of multiplication if you're thinking about the algebra of functions, if you're thinking of functions as like a set that you're going to do algebra with. I don't want to drown you in jargon, so I'm not going to say more than that right now. Let's take a look at an example where we're given some explicit functions f and g, and we want to compute these things and their domains. So the new homework set is homework 13, operations with functions. I have this set to be due the day you come back from spring break. So let's find something that is not super silly. How about something like number 6? I may change the question just a little bit, but we can write those two functions down, f of x is x squared minus 4x minus 5. And g of x, we can use just x minus 5. But instead of just computing f over g and its domain, we're going to compute some other stuff as well. So we're going to find, let's do f plus g, f minus g, f times g, f over g, all of them, and their domains. I want to start by observing the domain of the original function. So first, the domain of f the domain of f is all real numbers. It's a quadratic, it's a polynomial. So negative infinity to infinity. And the domain of g is also all real numbers. It's a linear function, that's a polynomial as well. So most of these are going to have domain all real numbers. Because if you intersect these two sets, you get all real numbers. The overlap here is everything. So start with f plus g. F plus g of x. The magic step for all of these problems is to first just write down the rule. As long as you do this, everything is going to feel easy, I promise. So every time you're asked to compute one of these combinations of functions, start by writing down the rule. All right, what is f of x? Well, it's x squared minus 4x minus 5. And I want to add to that g of x, which is x minus 5. My advice to you, put these things in parentheses. It's not going to matter here, but on the next one, and the one after that, and the one after that, it will matter. So if you always put these things in parentheses when you go to plug them in, you'll never run into a sign issue or a failure to distribute or anything like that. I can combine some like terms here. This is, if I just write these next to each other, x squared minus 4x, and then I've got a plus x here, and then minus 5 and minus 5. Negative 4x plus x is negative 3x, so this is x squared minus 3x, and then negative 5 minus 5 is negative 10. So that's the new function, f plus g of x. His domain, again, you see it's a polynomial, it's a quadratic. So the domain would be all real numbers, whether you're thinking about it on its own, like you're given this problem, find it fresh, or you're thinking about intersecting these two domains, either way. F minus g is next, and this is according to the rule, f of x minus g of x. And be careful here, again, make sure you use those parentheses, otherwise you'll end up with the wrong answer. So I'm subtracting all of g of x from f of x. That means I need to subtract parentheses x minus 5. And this negative is going to distribute. You'll have minus x and then plus 5. So if I do the same sort of thing here, this is going to be x squared minus 4x minus 5. Distributing that negative, I get minus x plus 5. And then combine like terms. Minus 4x minus x, that's minus 5x. So it's x squared minus 5x. And then I have minus 5 plus 5, that's 0. Ah, so I'm done. And again, the domain here, all real numbers, because polynomial. F times g is next. Now I go to the rule, just write down the rule and everything else will feel super obvious. F times g of x, the rule is that's equal to f of x times g of x. And again, you need to put these in parentheses. So f of x, that's x squared minus 4x minus 5. And I'm multiplying that by g of x, which is x minus 5. And I want to make sure I'm multiplying one whole function by the other whole function, so I put both in parentheses. This requires some distribution. We have to distribute, or it's kind of like foiling, but there's 3 terms in the first piece, so it's not exactly foiling. The general word for that is just distribute. That means I need to take this whole thing, multiply it by x, then take this whole thing and multiply it by 5 and subtract them. So I'm going to go ahead and write out what we get when we distribute. This will be x squared minus 4x minus 5 times x. That's this whole thing times this guy. And then we'll have, let's see, we can write it like this as minus x squared minus 4x minus 5 times 5. So this minus here is coming from this minus here. So I've got this whole thing times x, that's this, minus from this minus, and then this whole thing times 5, that's this. Now each of these needs to be distributed out. So I'm going to distribute this x across this quadratic. X times x is x cubed, minus 4x times x is 4x squared, minus 5 times x is 5x, minus parentheses. I'll just go ahead and distribute the 5. 5x squared minus 20x minus 25. And now I need to distribute this negative out front. So I get x cubed minus 4x squared minus 5x minus 5x squared. Minus here makes plus 20x. Minus here makes plus 25. And there are like terms we can combine, so we should combine them. I have minus 4x squared here, minus 5x squared here. That's minus 9x squared. There's only the one x cubed term, so I'll leave him alone out front. X cubed minus 4x squared minus 5x squared is minus 9x squared. And then x terms, I've got minus 5x here, plus 20x here. That's plus 15x, negative 5 plus 20. And then the constant term is just that plus 25. And you see what I was saying about polynomials being a ring, right? Here we added, subtracted, and multiplied 2 polynomials. Each time we got another polynomial out. And that makes finding domains easy. The domain of all or any polynomials will always be all real numbers, negative infinity to infinity. So that's the first 3. Any questions on how we came up with these answers? Okay. The next two are going to be a little more exciting. We're going to form the quotient f over g and find its domain. Oh, and we didn't do the composite. That's okay. All right, so we're just going to do the quotient still. Yeah, we'll look at some other stuff for composites. So this last guy, I expect him to have a different domain because the domain rule for f over g was different than the domain for the other three that we already did. Something that I hear a lot in office hours and stuff when we get to this section is people saying, I don't even know how to get started, right? What is this thing? How the fuck do I even get started on this? And that's why I say the rule, start with the definition, the rule. So that list of rules I gave you at the very start, that's always the place to begin for problems like this. So what the fuck is this? Well, f over g of x is by definition f of x over g of x. If you begin by writing this rule down, always be safe. And then I promise you, having done that, you'll be able to tell exactly where to go. I know what f is. F of x is x squared minus 4x minus 5. So that's what goes upstairs. And I know what g is. G of x is just x minus 5. And if I handed you this thing and said, find the domain, I'm sure everybody could do it, right? We just finished talking about rational functions. At the beginning of the semester, we did stuff like this too. The domain red flag here is the variables in the denominator. So we know that the bottom is not allowed to be 0. So we need x minus 5 to not be equal to 0. And that means x is not allowed to be equal to 5. So if I want to write that domain, there's a few ways I can do it. We talked about writing this in the set builder notation as we went through the section on rational functions. In set builder, that would be the set of all numbers x, such that x is not equal to 5. Or in interval notation, that would be negative infinity up to 5, union with 5 to infinity. We're just chopping 5 out of the number line. So either one of those would be a good answer for the domain. Any questions on this one? I'd like to try something with the composition operator now. Let's find f circ g. This symbol, by the way, the composition symbol, you'll hear me say circ, like circle. It's the way it's typed when you type it. Let's find f circ g and g circ f and their domains, where f of x is the square root of x and g of x is, how about 3 minus x. It's a good idea to start out just by finding the domains of the two original functions. So what is the domain of f? What's the domain of this function and why? Think about that homework on radical functions that we just did.
Would it be neither? I don't know.
So I want to ask, what sort of numbers can I plug in for x? Let's say that, let's talk about the other red flag, right? So the domain red flags that we have, there's two of them. Here, the red flag is you've got variables under an even root, right? The square root is an even root. It's like the 1/2 power. And if you have variables under an even root, what we need to make sure is that the stuff inside is not negative, right? If you plug like -4 in here, you'd get 2i out. You get imaginary numbers out. We don't want that. We want just real numbers. So when you have variables under an even root, the thing you always need to make sure is that the inside is greater than or equal to 0. That's the domain rule. So here that means x, that's the thing that's inside the root. X is greater than or equal to 0. So the domain f is 0 to infinity like this. Okay. So we've got two domain rules, right? It's not that hard to remember them. There's just two. If there are variables in the denominator, you got to make sure that stuff isn't 0. Right? You got to make sure that the bottom is not 0. And if you have variables under a square root, you need to make sure that the stuff inside the square root is greater than or equal to 0, right? Not negative. The domain of G, that's easy. G is also a G, like the previous examples, G is a polynomial. So that's just -infinity to infinity. All right. Now we were told to find f of G, right? F circ G and G of f and their domains. All we've done so far is find the domain of the two original functions. We haven't done any of those stuff the problem asked. So let's go ahead and find f of G. And like we said, the only reasonable place to begin is with the definition, with the rule. F circ G of x, or f of G of x, is f of G of x. It's what you get when you plug G of x into f. And I think the nicest way to do this is working from the inside out. The inside piece here, G of x, is 3 minus x. So f of G of x is f of 3 minus x. Everybody with me so far? All right, we're almost done. To finish this up, I need to say what f of 3 minus x is. And remember, this is not multiplication. This is not going to be the square root of x times 3 minus x. This is not multiplication. This is a function notation. This is f of 3 minus x. In other words, I'm going to take the formula for f, and instead of x here, which would put an x here, I'm going to put 3 minus x here, which means I'm going to put 3 minus x here. So this is going to be the square root of 3 minus x.
What was the point in writing the first, like above the square root?
This guy?
Yeah.
I think it can be helpful to break these things down into steps. So depending on how complicated each of the functions f and g are, it can be a little bit tough sometimes to jump straight to this. If you see this right away, that's okay. But this is just explicitly saying, what is the inside? The inside is 3 minus x. Okay, and then what is the outside? The outside is the square root. Okay, that means the whole thing must be the square root of 3 minus x. But if you can go straight from here to here, by all means.
Okay, so the square root is the f.
Correct. Yep, f is the square root function. So f takes whatever you feed it and puts that in a square root. So when we feed it 3 minus x, he puts 3 minus x in the square root. Kind of the, there's a silly thing I like to say to help some folks with this. Silly note. All right, f of x, that's the square root of x. So, f of 4 would be the square root of 4. F of pi would be the square root of pi. F of dog shit would be the square root of dog shit. And f of your mom would be the square root of your mom. All right, this is kind of a way to help understand function notation. F of anything is the square root of that thing. So the step from here to here, we say, okay, f of 3 minus x, well, that's got to be the square root of 3 minus x. Okay, so are we all comfortable at how we arrive at this expression for f of g? Are there any questions about how we arrive at that expression? Doing good? Okay, we still have to find the domain of this thing. And that same domain red flag, that same domain rule that was guiding us in the first part here will guide us down there. So to find the domain, again, we just need the inside of the square root to be greater than or equal to 0. And this time that inequality requires a little bit of work. The inside of the square root here is 3 minus x. So I need to set 3 minus x greater than or equal to 0. And there's a few ways to solve this. I think what most people would do is subtract the 3 over, and that's okay. That'll give me negative x is greater than or equal to negative 3. And then divide both sides by -1, get rid of the negative. And remember, when we do that, the inequality is going to flip over. So here's the domain as an inequality. And if I want to write that in interval notation, this is all the x's which are less than or equal to 3. So in interval notation, that would be -∞ up to 3 with a bracket. Any questions on the domain here? Okay. We also wanted to compose in the other direction. We wanted to find G circ F as well. So let's go ahead and do that. Neat fact about the composition operator, it is not commutative. F of G and G of F can be totally different functions. So when I compose in this order, G of F of X, well, that's G of F of X, like this. Now the inside function is the square root, and the outside function is 3 minus x. So this is going to be G of the square root of x, because that's what this inside function is. Also, something else now. And then to finish this up, I need to figure out what G of the square root of x is. And you can play that same silly game, like G of 2 would be 3 minus 2. G of pi, well, that would be 3 minus pi. G of some crap would be 3 minus that crap. Right, and G of, let's go with your mom again. 3 minus your mom. So what is G of the square root of x? It's going to be 3 minus the square root of x. Right? G of anything is 3 minus that thing. So G minus root x, sorry, G of root x is 3 minus root x. And notice that the domain here is going to be different also, right? The domain of f of g was -infinity up to 3. The rule we apply to find the domain is the same, but the result is going to be different because the inside here of the square root is different. Remember when we talked about radical functions before, the numbers, stuff going on outside the square root, that doesn't have any effect on the domain. So for this function, this 3 isn't going to play in the domain at all. The only thing that I have to worry about is the variables under the square root. So again, we need to set the inside of the square root greater than or equal to 0. Only the stuff inside the square root has any effect on the domain. And here, the inside is just x. So the domain is all x's that are greater than or equal to 0. It's the same as the domain of f. Any questions on finding G of f and its domain? Okay. Because we're going to build with this composition operator, eventually what we're going to do is define the word inverse for functions, which is different than like reciprocal. in order to define that notion of inverse, which is going to be a big deal for us, especially when we talk about things like exponential functions and logarithms, because the only way those are defined is as inverses of each other. It's going to be important because it's defined in terms of the composition operator to have a somewhat deep understanding of the composition operator. So if you want to understand what f circ g means in relation to the functions f and g, there's a few ways you can do this. My favorite is using something called a machine diagram. So functions can be represented as kind of like machines on an assembly line. Inputs come in, the machine is the function, the machine does something to that input, and then it sends out an output. So if you think of the F machine on an assembly line, what the F machine does over here is the input side. It takes in X's. It does something to them, that maybe it takes the square root, maybe it adds 7, maybe it multiplies by 5 and then divides by 12, whatever. Takes in some input X. That X comes into the F machine, the machine does something to it, and then it spits something out. And the thing it spits out is F of X. It's the output associated with the input X. So inputs come in, outputs go out. G also has a machine diagram, right? We could draw this picture just using the letter G there instead. X's come in, G does something to them, outputs go out. These machine diagrams are a useful tool for understanding the composition operator because composition is plugging one function into the other. So what is f of g? Well, that's what you get when you take g and you plug it in as the variable or the input for f, right? We saw that back here. Here's f of g. How did we find f of g? Well, I took f, and instead of plugging in x, I plugged in g of x. So I'm using g of x, the output from the function g, as the input for the function f. I'll say that again. The way you find f of g is by using the output from g and plugging that in as the input for f. So what does that mean in terms of machine diagrams? That means I'm going to take this machine and put it over here as the input for f. So here's the fog machine. You take the G machine, X's come in, G of X's go out. You take the F machine, normally X's come in and F of X's go out. but something a little different is going to happen here because I'm going to connect these to each other. So now, instead of x's coming into the F machine, g of x's are coming into the F machine. And the F machine does what it's always done. Whatever you feed it, it spits F of that out. So what's going to come out here is F of g of x. This is what the composition operator does. It glues the two machines together. And this whole thing, if you put this all in one box, this would be the machine diagram for the function f of g. X's come in, f of g of x's go out. And what's going on inside that machine is that you've taken the G machine and you've hooked it up as the input, taken the output from the G machine and hooked it up as the input for the F machine. This is what composition does. It might seem like a really abstract notion, but it is the correct notion. I'll give you a minute to draw, write, ask any questions we have. Annotate here. The inputs for this machine are still x's. Output is f of g of x. Composition operator here is like where you glue these two things together. Cool, right? I was like, this has always made me happy. Oh, you want a gross metaphor? Here. I think this metaphor might be aging a little bit because I don't know if you guys have seen the movie. Honestly, I haven't seen the movie, but I'm aware of it. F of g is the human centipede of functions, right? You take the output from one and you attach it to the input from the other. You guys are familiar with the human centipede? That's what this is, right? We're gluing the ass of G to the mouth of F. Gross, I know, but that's what's happening. Okay. Disgusting metaphors aside, there is another way you can think of this. And that's what's called mapping diagrams. So these are machine diagrams. The other kind of standard tool for visualizing these are what are called mapping diagrams. So the mapping diagram for F on its own, we have two sets here. The set on the left is the domain of F. The set on the right is the range of F. And what F does is it maps elements from the domain into elements of the range. So F here is the arrow. There's actually a whole field of mathematics that just studies diagrams like these, like with arrows and which way they point. It's kind of silly, but don't tell any category theorists I said it was silly, but it's called category theory. The mapping diagram for G is the same sort of thing. G has its own domain and its own range. And G takes elements of the domain and sends them into elements of the range. A mapping diagram for F of G, kind of like the machine diagram, you identify this thing with this thing. You just scooch these guys together until the range of F sits on top of the domain of G. So if I take this original domain for F, now that F send that thing into an element of the range of F. And then I scooch G over so that this is now the domain of G. Here's F, here's G. Then this is going to hit something over here. This would be, I've done it in the other order. This would be G of F of X. And if you think of there as being just a single map, just a single arrow going from here straight to here, that would be G of F. That's the idea. So same sort of thing. I think the machine diagrams are a little bit easier to understand than the mapping diagrams, but I have to show you both because you'll encounter these in this and future math classes. All right, that's enough of being really abstract about this shit. Let's go back to solving some particular problems and let's try something. We should have some with a table in here. Yeah. We haven't talked about what one-to-one means yet. Oh. Oh, we don't have anything straight up tabular, do we? All right, let's make one up. Example. Let F and G be described by the tables. So it's X and F of X. We'll keep this simple. And we'll say F sends 0 to 3, sends 2 to 0, and sends -7 to 5. And you will have X and G of X. And let's say G sends 0 to -7, sends maybe sends 5 to 2. And let's do here, how about 3 to 0? Okay. So here's two functions described by tables. And let's find F circ G of 5. Let's find G circ F of 2. We can find, let's see, G of G of 3. That's enough. We'll just do these. Okay. So I don't have algebra expressions that I can plug in, right? I'm not going to get a formula here. So we need to work just with the tables and with the definitions. How should I get started for this first guy? What's the safe way to get started on any problems like these?
Break it up.
Yeah, break it up, like just write down the the definition, the rule, right? Which is I think what you mean by that. So if I kind of break this out using the definition, f circ g of 5 is by definition f of g of 5. And then if I look at that first table, again, like the previous examples, we need to work from the inside out. So we start with the definition and then work from the inside out. I can't possibly say what f of g of 5 is without knowing what g of 5 is. So what is g of 5? What is this thing?
2.
Very good, it's 2. So f of g of 5 is f of 2. Because g of 5 is 2. All right, when x is 5, g of x is 2. That means g of 5 is 2. In other words, g maps 5 to 2. All right, now we're almost done. If I want to know what this is, I now look over to the table for f, because we're just asking what is f of 2? Okay, well, f of 2, when x is 2, f of x is 0. So f of 2 is 0. So f of g of 5 is 0. Not too bad. Always start with the rule and then work from the inside out. But always start with the rule. All right, let's try this with the second guy. What would be my first step here? What would I write down?
The g of f2.
Yeah, very good. G circ f of 2 is, we just write it in that function notation, g of f of 2. F of 2 we computed a minute ago. F of 2 is 0, right? When x is 2, f of x is 0. So this is g of 0. And then we look at the table for g, g of 0. Okay, g of 0 is -7. So g of f of 2 is -7. This last one's kind of fun because we're composing a function with itself. And you can do that. You can compose functions in any order you want, as many times as you want. So the first step here would be to write g of 3. And then you work from the inside out. So the inside here, g of 3. G of 3 is 0. And then just like in the last guy, g of 0, that's -7. Not too bad. Okay. There's one more concept I need to level with you on here, and that's this idea of a function being one-to-one. So a function is called one-to-one if it sends every input to a unique output. You know, the definition of a function is that each input goes to one and only one output. If I want to narrow that down a little bit, if I want to put an even tighter restriction on what functions are allowed to do, I can require that every output come from only one input. So a function, I'll call it f, is 1-to-1 if different inputs lead to different outputs. There can be a lot of sort of word salad here. And I think this is the way to say it that makes the most sense. Algebraically, we could say this a few different ways. You can say if x is different from y, I have two different inputs, x and y, then f of x will be different from f of y. So if you have two different inputs, they have to go to different outputs. And this is equivalent to saying if f of x is equal to f of y, then x must be equal to y. If you have two outputs that are equal, then they had to have actually come from the same input. So these say the same thing. And all three of these say the same thing. In plain language, we say different inputs lead to different outputs. The most natural way to write that down in terms of algebra symbols is if x is different from y, then f of x is different from f of y. And you can take what's called the contrapositive of that statement, which is the bottom one. If f of x is equal to f of y, then x must have been equal to y. So that's the algebraic characterization. There's also a graphical. A function whose graph looks like this will be 1-to-1, because if you take any two different inputs, say x here and y here, they go to different outputs. This would be f of y, and this over here would be f of x. This is 1-to-1. Kind of graphically, the more interesting thing is to ask yourself, what does it look like for a function to not be 1-to-1? So if you have a function that does something like this, not necessarily a parabola, but just anything looking remotely like that, then it is possible to find two different inputs, x and y, where f of x and f of y, the outputs are the same. And there's a nice test for this associated with the graph. There's a nice way to test from the graph whether a function is or is not 1-to-1. So this is not. 1-to-1. If you look at what's going on in the not 1-to-1 picture, the fact that there are two different inputs that lead to the same output, two different x values that lead to the same y value, that's the same as saying that this blue line hits the graph more than once. And if there's any horizontal line that hits your graph more than once, then the function graphed is not 1-to-1. This is called, and I'll stop here. This is called the horizontal line test. It is a test for figuring out whether a function is 1-to-1. It just says if any horizontal line hits the graph of f of x more than once, then f is not a 1-to-1 function. And what we're going to see when we come back from break is that being 1-to-1 allows us to do something very special with that composition operator. I won't lay that on you right now, but the composition operator very much likes 1-to-1 functions and very much does not like functions which aren't 1-to-1. But this is it for now. So there is a homework set open for you. It's set to be due right now on the Monday you come back from spring break. Tomorrow is the makeup session for the test. So if you missed the test on Tuesday for whatever reason, either because you asked to delay it or because something crazy happened or you just slept in or whatever, then you need to come to my office hour tomorrow to make up the test. That's the only session, makeup session I'm going to be offering. If that doesn't work for you, or for some reason you cannot come tomorrow and you missed the test on Tuesday, then you need to send me a Canvas message so we can make some sort of arrangement, but we're going to need you to take the test before break. That is it for me for today. Any questions for me before we wrap up here? Okay, then keep an eye on Canvas announcements over the break. I'm toying with the idea of maybe giving you a little project or something to work over the break, just to try and keep you in math land a little bit. Please do be safe. Don't do anything crazy. If you do something crazy, don't record it. Be safe, be smart, enjoy your breaks, think about math a little bit, make sure you get the homework done, and I will see you guys on the 14th. Chatty, yeah, I do have I have an office hour at 11, so if you want, we can chat over there. I'll be starting that in about 12 minutes. All right, that's it from you guys. Take care, be safe.